One hot encoding can bloat features and still miss signal. You'll use CatBoost in Python to handle categorical variables cleanly and build a stronger tabular model with less preprocessing. This is the setup you'll be able to run after this, which trains on categorical fields and predicts a label for a new record with confidence. I'm Professor Pi, teaching AI foundations with simple Python. CatBoost is a gradient boosting library that knows categories natively. People reach for it when they have text-like labels, cities, devices, or any non-numeric fields. The alternative is to one-hot or label encode and then hope decision trees learn the right interactions. That workflow can explode dimensionality or leak information. CatBoost saves time and often improves accuracy for modest-sized tables. Think of a tiny customer table with city, device type, and age bracket. You want to predict a binary outcome like conversion. Success is a model that uses the category patterns directly, needs less manual feature engineering, and serves stable probabilities for new cities or devices. CatBoost handles unseen categories at inference, and it builds trees that split on smart category statistics. At a high level, CatBoost converts category values to useful signals by learning target-aware statistics inside the training loop. That means the model looks at how each city or device correlates with the outcome while avoiding naive counting leaks. It then uses gradient-boosted trees to combine those signals. Strengths are low setup cost and good performance on mixed data. Weaknesses are the need to tune tree depth and iterations to avoid overfitting on very small datasets. We will build a focused demo. It trains on a tiny in-memory table with city, device, and age. Then checks a held-out pair and examines feature importance. Finally, we try a deeper model and a production-friendly version with early stopping to show how predictions change. This keeps the ideas concrete and lets you see how CatBoost treats categories before you scale it up. Now, we'll fit a minimal model. This snippet fits a tiny CatBoost classifier directly on raw categorical features and predicts a probability. A small in-memory table is created with city, device, age, and a binary target. The pool object wraps the first 4 rows for training and marks the first 2 columns as categorical using cat features. The CatBoost classifier learns simple target statistics over categories without one-hot encoding and then fits trees. After training, predict proba on the remaining rows returns class probabilities, and we extract the first example's positive class probability. Increasing iterations, or depth, generally yields more expressive models, but risks overfitting on very small data. The printed probability confirms end-to-end training and inference without manual encoding. Next, we'll check basic accuracy on a held-out pair. This example evaluates accuracy on a small holdout using CatBoost's pool and predict. It constructs a test pool from the last 2 rows to ensure CatBoost applies the same categorical treatment as during training. The model M predicts class labels over that pool with predict, returning an array of 0s and 1s. The code compares these predictions to the held-out targets and computes the mean match rate as accuracy. Because pool tracks which columns are categorical, feature processing stays consistent between training and evaluation. The printed accuracy shows how well the first simple model generalizes, giving a quick, production-minded sanity check. Now we'll inspect what the model relied on. This code inspects what CatBoost learned by ranking features via getFeatureImportance. It asks the trained model M for importance values computed on the original training pool, returning 1 score per input column. The list names maps positions back to human-readable columns for city, device, and age. The code finds the index with the highest score and reports both the feature name and its numeric importance. Feature importance here reflects how much a feature splits help the model reduce loss. The printed top feature and score quickly explain which categorical signal the model relies on most, guiding simpler, safer pipelines. Next, we'll tune depth and iterations to see the directional effect. This snippet tunes CatBoost by increasing depth and iterations, then measures how the change moves a specific test probability. It creates a new model M2 with a deeper tree depth and more boosting rounds, which can capture richer category interactions. After fitting on the same training pool, it predicts the positive class probability for the same test row as before. The code computes the difference between the tuned and baseline probabilities to highlight the directional impact of the hyperparameters. Increasing depth often improves fit, but risks overfitting. More iterations should be paired with lower learning rates. The printed shift shows a concrete behavior change from tuning. Now we'll train a production-friendly version and serve unseen categories. This snippet trains a production-friendlier CatBoost model with early stopping, and then serves predictions on unseen categories. It enables use best model with OD type and OD weight, so training halts when validation stops improving. The model final M fits on the training pool with test pool as eval set to pick the best iteration. A tiny new DF includes a new city and a new device, demonstrating CatBoost's ability to handle previously unseen category values at inference. The code computes the average predicted probability for these rows and also reports the number of trees actually used. The printed values show a compact model selected automatically and stable serving outputs. In a real project, this toy flow maps directly. Your training set becomes a larger CSV or database extract. The pool still wraps the same columns and tells CatBoost which features are categorical. The early stopping pattern scales to larger validation sets and keeps model size reasonable for serving. Recap: CatBoost is a gradient boosting tool that natively handles categorical features and reduces preprocessing. Use it when you have mixed-type tabular data and want to skip one-hot explosions while keeping strong predictive power. Caveat: tune depth and iterations, and watch for overfitting on tiny datasets. Next step: try tuning learning rate and tree depth together, and compare validation metrics to pick a robust model. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.